Welcome to the lecture devoted to exploration. Part of the material presented in this lecture is taken from the following book, while transcription and interpretation errors are responsibility of the lecturer. This lecture introduces the following concepts: summary statistics with specific reference to mean and mode, to percentile and quantile, to range, variance and standard deviation, to absolute average deviation, median absolute deviation and interquartile range. The lecture also provides basic tools for visualization as histogram and box and whiskers. After having downloaded and opened the churn.txt file, you started its inspection. So you started to analyze the portion of the file that your friend, the CEO of the telecom company, sent to you. Your friend asked you to provide the most basic summary of the data in such a way to gain a general picture of how the churning process is progressing. To fulfill the request of your friend, you make the decision to first compute summary statistics for all the attributes reported in the churn.txt data file when this is meaningful. To show how to compute summary statistics for different types of attributes, we start by considering the churn attribute. The churn attribute is a qualitative one and in particular a special case of qualitative attribute. Indeed, it is a binary attribute because it can take only two different values. According to what we have presented and discussed in the lecture on data type, you can summarize the churn attribute by computing its mode, so by computing which is the most frequent value in the dataset. Here and in the rest of the lecture we will make the assumption that the available dataset is represented just by these 10 records. So to show how to compute the mode for the churn attribute, we proceed as follows. We first find that the two different values for the churn attribute are n and y, standing for no and yes. We then inspect the observation of the available dataset and find how many times the attribute churn is equal to n and how many times it is equal to 1. And we discovered that we have 9 records where the churn attribute is equal to n and just 1 record where the attribute churn is equal to y. So we know that 9 and 1 are the absolute frequency of the churn attribute with specific reference to the value n and to the value y. From this absolute frequency, which sums up to 10, which is indeed the number of records of the considered dataset, we can compute the relative frequency. The relative frequency of n will be equal to 9 to 10, so it will be equal to 0.9, while the relative frequency of y will be equal to 0.1. And again we have that the sum of the relative frequencies must be equal to 1. We now focus the attention on the day-means attribute, which is a quantitative attribute, and so we have to consider a different summary statistics than the one used for the churn attribute. In particular, we will use the quantile summary statistics. To this extent, so to show how to compute the quantile of the day-means attribute, we proceed as follows. we take all the values of the day means attribute. We also have to point out that we have a missing value, so we will have 9 observations, 9 different values which are reported here, and we simply sort from the smallest to the greatest these values to obtain this sequence, this order of the values for the day means attribute. Then we can state that 166.7 is the quantile of order 1/3 for the attribute day means. Indeed, 166.7 is such that 1/3 of the data points is smaller or equal than it. In the same manner, we will say that 223.4 is the quantile of order 2/3 of the attribute day means, because 2/3 of the available values of the available data has a value which is smaller or equal than 223.4. A very special type of quantile is the median, in our case equal to 218.2. The median is particular because it is such that exactly the same number of observations of the available dataset have a value which is smaller or greater than it. So in our case we have 9 observations and we have that exactly 4 have a value which is smaller than the median and exactly 4 have a value which is greater than 218.2. The median is formally defined to be the quantile of order a half. For quantitative attributes, you can also compute the mean. In particular, the mean of the attribute day means is computed as follows. So is the average value of the 9 observations from x1 to x9 which are available in the dataset for the attribute day means. In particular, the mean of day means is equal to 213,26. However, you know that in general the mean is sensitive to anomalous records, so to the so-called outliers, while the median is a more robust estimate of the middle of a set of values. In our case, we have that the median was computed to be 213,26, while the median was computed to be equal to 218.2. So in our case, these two values are not that far, and probably this is due to the fact that there are no strong outliers in the dataset we are taking into account. Another possibility to achieve robustness with respect to outlier observations is to use the trimmed mean. To introduce the trimmed mean, we use this order x1, x2 up to xn, so we use the available data sorted from the smallest to the greatest. To compute the trimmed mean, we simply remove the smallest and the greatest value of the attribute day means. Then we compute the mean of the observations from x2 up to x8 to obtain the trimmed mean, which is equal to 208,98. Another set of used summary statistics for quantitative attributes are those that measure the dispersion or spread of a set of values. The first one is the range. To show how the range is computed, we again use the available data sorted in increasing values from x1 up to x9. It is trivial from this order to state that the minimum value is equal to 157 while the maximum value is equal to 299.4. Minimum and maximum value are then used to compute the range. The range is simply the difference between the maximum value and the minimum value, and in this case it will be equal to 142.4. However, it is worthwhile to mention that the range can be misleading if most of the values of the attribute are concentrated in a narrow band of values. Therefore, we usually prefer to compute the variance. The variance of the available data for the attribute day means is equal to 2496.5, and it is simply computed as 1 divided by the number of observations minus 1 times the sum of the square difference between each observation and the mean value of the attribute. However, it is often the case that we report the standard deviation in place of the variance, where the standard deviation sigma is simply the square root of the variance. This is because the standard deviation takes the value on the same scale as the original attribute to be analyzed. It is important to point out that the variance depends on the mean, and thus it is also sensitive to outliers as the mean is. Therefore, more robust estimates of the spread of a set of values have to be provided, for example using the absolute average deviation, which is typically indicated with AAD, and which is computed as shown here. In particular, we replace the square difference, simply with the absolute value of the difference of each observation with respect to the mean of the considered attribute. An additional quantity which is robust with respect to outliers is the median absolute deviation, which is typically indicated with MED, and it is simply the median of the absolute values of the difference between each observation and the mean of the attribute. Also, interquantile range, often indicated with IQR, is a robust estimator for the spread of a set of values. Now we make the assumption that on the overall dataset 166.7 and 243.4 are respectively the 25th quantile and the 75th quantile. They are also called the lower quartile and the upper quartile. The interquartile range is defined as the difference between the upper quartile and the lower quartile, that in our case is equal to 76.7. When multiple quantitative attributes are available, you usually compute the variance-covariance matrix, where the covariance between two quantitative attributes x and y is defined as shown here, where m represents the number of observations for the pair x and y, while x overline and y overline represents the average value for the values of the attribute x and the attribute y. We also have to notice that the variance-covariance matrix is a square matrix, and it is symmetric in the sense that each element ij is symmetric to the element ji, and contains the value of the covariance of the ith attribute with respect to the jth attribute. Another measure of association between pairs of quantitative attributes which does not depend on the variance of each attribute is the linear correlation coefficient, also known as the Pearson correlation coefficient. It is defined as follows. The correlation of x and y is equal to the ratio between the covariance of x and y divided by the square root of the product of the variance of x and y. The linear correlation coefficient ranges in -1 plus 1. The greater it is in absolute value, the stronger it is the linear relationships linking the two attributes x and y. When exploring a dataset, you also make the decision to exploit data visualization. It has to display information in a graphic or tabular format. There are many tools for graphical visualization, but we will show here just very few. In particular, histogram. Histogram is a plot that displays the distribution of values for attributes by dividing the possible values into bins and showing the number of records that fall into each of such bins. Histogram in the case of a quantitative attribute is such that each bin is associated with an interval of values and bins can have the same width or not. Here we report a first example of histogram. In particular, it is related to the continuous attribute age, and on the x-axis we have the values of the age, while on the y-axis we have reported the count, so the number of observations of the dataset that fall in each of the intervals that have been defined by the histogram, so in each of the bins that have been defined. However, is a rule of thumb that we usually require for the histogram that each bin contains at least 5 observations, and so here on the right we show what happens if we change the width of the bin. So we increase the width of the bin, trying to fulfill the requirement of having each bin to host at least 5 observations. However, also in this case we fail, and so we have to increase further the width of each of the bins. In the case of the histogram, when applied to qualitative attribute, then we have that each bin is associated with a specific value, so a possible value of the qualitative attribute. Furthermore, when the values are too much, they are aggregated to possibly form a meaningful bins, so a bins which is meaningful for the analysis. Here we show the histogram for the attribute country, which is a discrete and in particular a nominal attribute, which can take 3 values, which are Japanese, American and European. So on this left axis we again have reported the number of observations falling in each of these bins, so the number of cases where the country is equal to Japanese, equal to American or equal to European, while on the right axis we directly report the percentage, so the relative frequency for each of the 3 bins related to the country attribute. An extremely powerful and widespread used tool for graphical representation is offered by the box and whiskers, also known as box plot, which applies only to quantitative attributes. We report here an example of a box and whiskers for the continuous attribute named weight. On the graphical representation of box and whiskers, we can identify different elements. The first one is the median, which is also known as the quantile of order 50. Then we can identify the lower quartile and the upper quartile, which have been already introduced before. According to the definition, we have that dq represents the interquartile range. Concerning the whiskers of the box and whiskers plot, different interpretations are possible. In the first one, we have that the two whiskers are associated with the smallest value that is not an outlier, so it is greater than QL minus 1.4 times dq, and this other whisker is defined as the greatest value that is not an outlier, and it is smaller than QU plus 1.5 times dq. In the second interpretation, the whiskers are associated with the minimum and with the maximum value in the dataset. In a third interpretation, this whisker is associated with the 10th percentile, while this whisker is associated with the 90th percentile.